Vivemos em um planeta interconectado, não apenas pela velocidade com que trocamos informações, mas porque tudo o que fazemos impacta na vida uns dos outros. Isso valoriza uma das coisas que mais nos faz humanos, o trabalho coletivo. Somos uma espécie de realizadores, com alta capacidade criativa, que pode sim mudar os rumos do planeta. Podemos fazer diferente usando a tecnologia para nos tornarmos mais eficientes, otimizando nossos recursos, evitando o desperdício e transformando a vida de todos. A Unesc acredita na conexão do conhecimento e da comunidade, da ciência e das grandes ideias, dos olhares e das diferentes realidades, de pessoas e propósitos inspiradores. Venha construir o amanhã com a gente. Unesc, uma universidade de conexões. Matrículas abertas para os cursos de graduação presencial.
Uma boa tarde a todas e todas. Sempre atenta ao cotidiano do Sul Catarinense, a Unesc, há 53 anos, tem a missão de transformar a vida das pessoas e o ambiente em que vivemos, trabalhando a integração entre ensino, pesquisa, extensão, internacionalização e cultura. A pesquisa é um desses 5 importantes eixos da nossa universidade comunitária. E o primeiro simpósio de sepse, promovido pelo Laboratório de Fisiopatologia Experimental da Unesc, reúne, nesta primeira edição, profissionais da área da saúde para discutir sobre os avanços nas pesquisas e abordagens clínicas da sepse. O evento visa promover com excelência e qualidade científica atualizações acerca do tema, proporcionando uma rica troca de experiência multiprofissional. A sepse, embora seja uma das causas mais comuns de mortalidade hospitalar, muitas vezes não é debatida amplamente no ambiente acadêmico. No Brasil, poucos são os grupos de pesquisa que se dedicam integralmente aos estudos sobre sepse. No entanto, um dos intuitos deste evento é aproximar a comunidade acadêmica e os profissionais de saúde com as pesquisas que vêm sendo desenvolvidas sobre a sepse e suas complicações. Desde já, nós agradecemos a participação de todos que nos acompanham ao vivo aqui no canal da Unesc TV no YouTube. Serão 3 dias de seminário e todas as palestras serão transmitidas pelo YouTube. Nós gostaríamos de lembrá-los também que ao final de cada palestra estaremos colocando um QR Code na tela e também o link no chat para a confirmação de presença. Então, fiquem atentos que, ao final de cada palestra, nós estaremos colocando aí tanto o QR Code na tela, quanto o link no chat para a confirmação de presença no simpósio. Nosso primeiro convidado é o Dr. Mervyn Singer, professor de Medicina Intensiva na University College London. O Dr. Singer é autor da atual definição de sepse e choque séptico. Liderou uma série de importantes ensaios multicêntricos em cuidados intensivos. É autor de vários artigos e livros e pesquisador. E o tema dessa primeira palestra é Sepse, Past, Present and Future. Essa palestra está sendo realizada justamente neste horário por causa do fuso horário do nosso palestrante, né? Estamos aí nos adequando e para ter o privilégio de ouvir essa palestra. Antes de passar a palavra ao mediador, que será o professor Dr. Felipe Dalpizol, eu preciso lembrar que você também pode participar dessa palestra, deixando aí no chat o seu nome e a pergunta, que ao final da palestra estaremos abrindo para o debate. Os mediadores, o pessoal da organização vai estar acompanhando o chat e vai estar também abrindo essa possibilidade para o debate. Eu passo a palavra agora, então, para o professor Dr. Felipe Dalpizol, que fará a mediação e também pode apresentar aí com mais propriedade o nosso primeiro palestrante desse seminário. Boa tarde, professor. Agora é com você. Professor, seu microfone está desligado.
Eu tinha desligado antes, tá certo, obrigado. Obrigado, Janine, pela apresentação do evento e pela apresentação do nosso primeiro palestrante. A gente vai ter a abertura oficial mais tarde, então não vou me alongar muito falando a respeito do simpósio nesse momento, vou deixar isso para o próximo momento à tarde. E gostaria de reforçar aqui que é um grande privilégio poder ter o professor Mervyn Singer aqui conosco, ele que é certamente um dos pelos 5 grandes cientistas em sepse no mundo e portanto, e por isso ele foi um dos cabeças da nova definição da sepse que está em vigência desde 2016, o primeiro autor do paper da nova definição de sepse, além de ser uma pessoa extremamente inteligente, disponível, simpática, é um grande amigo nosso de algum tempo. Então, de coração, by heart, I wanted to say thank you very much, Singer, to be here with us. It is a great pleasure to have you here. And hopefully in the next one you can come here and we have a face-to-face meeting. You will be always welcome here in Criciúma. Then it's your time to.
Great, thank you. I'll just share my screen. Let me just share the screen. Right, so hopefully. Right. Okay. Yep. Is that good? Can you see that all right?
Yeah, it's good.
Lovely. Perfect. Right. So, Felipe, thank you very much indeed for the lovely invitation and the really kind words. It's a great pleasure to, join you all in Brazil. And, we've been through a bad 18 months. And as you say, it's nice to get back to normality. I'm currently in my first face-to-face meeting at the moment in 18 months. I'm in Belgium at the moment. So what I'm going to talk about is looking back in the past in translational research to understand how we can go forward to have new leads, new therapies. When you go to PubMed and put in sepsis and species and therapy, and I looked at this last year, you can see there are thousands of papers on sepsis for rats, mouse, dog, rabbit, baboon, and the red bars show those where there's been an intervention, a therapy. So approximately half of the studies have involved some type of intervention, and as you can see, there's thousands of these publications. And many of these models show a survival benefit from a whole variety of interventions. So you can go through lots of papers all showing better survival for the animals. However, when it comes to how many of these products have come through to human beings and are now being used routinely, the cupboard is empty. And as you see from our experimental mouse, he's reassuring the patient, don't worry, I had the same drug and it cured me, but not necessarily so. And this came from Jean-Louis Vincent here in Belgium a few years ago, and basically found they did a literature search and there was no clear evidence that any drug therapy has made a difference in critically ill patients. I'll talk a little bit about COVID later on. So where have we gone wrong from animal models to patients? And I wrote this with a good colleague of mine, Alex Dyson, over 10 years ago. And we mentioned that there are problems with animal models, the type of insult they're given, the duration of the model, what supportive therapy, do they get fluid, do they get antibiotics? So we need to try and make them as close as we can to the human patient condition. And again, if we can improve upon this, it may translate better to clinical use. And I was on this working group which reported a few years ago. This is a sort of summary slide, but we looked at making lots of recommendations as to how to improve animal models for sepsis to try and make them more representative of real life patients. So I'll just briefly touch on some of these with two papers just to make the point. There are lots of different issues. The models vary in severity, the type of species, the age of the animals, comorbidities, type of insult, the sex, male, female, the ethnicity, the duration of the model, what treatments are given alongside, like fluid, antibiotics, when you give the intervention relative to when you induce the septic insult. So let's look at severity. This is an old paper, but in the early days of anti-TNF therapy, interleukin-1 receptor antagonists, so these were the early days. By 2002, there were 22 trials in human sepsis. And the authors, they came from the NIH in America. They found that there were published 38 animal studies of sepsis which supported the role or going to man. One of the big things they noticed was the animals, the control group of animals was much more severe. On average, a median 88% mortality, whereas when it got to patients, the mortality rate was much lower, 39%. And they found that regardless of what septic insult, when you gave the drug, how much you gave, the type of animal, the duration of the study, survival improved as the animals got sicker. So I'll explain this graph. So odds of dying are the sort of control group mortality on a logarithmic scale, and the odds ratio are the survival benefit. So anything going up represents better survival. The animal studies are shown in the circles. So if the animals had a high control group mortality, there was this correlation between increasing severity and better response to the drug, the intervention. On the other hand, there were a few models where there was a low mortality rate, and here the drug caused harm, not benefit. And in the middle, the diamonds are the human studies, and you can see they fall in the middle. So they have about a 30, 40, 50% mortality, and there is no benefit from the drug. So they suggested that the animal model needs to reflect more about the human situation. I'll talk about age, sex, duration, fluid, antibiotics, timing in the next study. They all come nicely together into this nice study from a group in America. And they used a variety of mice, male, female, old, different types of mice, etc. And they gave them a peritonitis insult, and then they waited until the animals started to deteriorate. And the deterioration was a drop in the heart rate and a drop in their body temperature. Mice become hypothermic when you make them septic. And they had different treatments, one dose of an antibiotic, a bolus of fluid, or both. And they gave the fluid or the antibiotics at the time the animals were deteriorating, or they waited 2 hours or 4 hours. So you had delay in treatment built in. And what did they show? Well, if you look at antibiotics, so the thicker bar shows waiting 4 hours, and the very light bar shows giving the antibiotics when the animals became ill. So if you stop the study at 3,000 minutes, that would look very impressive that antibiotics work. If you delay 2 hours, 4 hours, the animals do worse. However, importantly, they allowed the model to go to 6,000 minutes. The same happened with fluid. If you didn't give any fluid, the animals died, or virtually all died by 1,000 minutes, whereas about 50-60% were still alive if they received fluid in the as resuscitation. If you let the study run on, unfortunately, you can see that all the antibiotic did was just delay the time to death. The animals all died, they just took longer to die. And the same with fluid. The animals all died, they just took longer to die. When it comes to males against females, here the females showed no difference in mortality, whether or not they got the antibiotics immediately or after a 4-hour delay. So they were different from the males. I'll come back to that later on. Old mice, again, there was a brief delay, but they still nearly all died if they got the antibiotic 4 hours later. So it basically just gives some very nice lessons. And so I make the point that even animals are not created equal. You have a variable response to the same insult despite using similar animals. They are the same strain of animals, the same age, the same sex. They're brought up in the same way. So let's talk a little bit about enrichment, prognostic stratification. So let's assume we have an animal model, a rat model, Wistar rats, that's the strain. They're the same age, about 3-4 months old, the same sex, all boys, the same upbringing. They're brought up the same way. And you have a model that gives a 50% mortality. So my question has been, why do half of these identical animals live and half die? And can you predict the ones who will do well and the ones who will do badly, and do they act differently? And we did this all years ago, our first study. This is Alain Rudiger in the lab doing some echo measurements. At the time we had this really big machine, and this is a male rat model, fecal peritonitis. It runs for 72 hours and they get continuous intravenous fluid resuscitation. And the 72-hour mortality in this model was 25%. And we found that doing an echocardiogram at 6 hours under a brief period of anesthesia, you could distinguish the animals that would go on to live. They had a good stroke volume. They had a 20% mortality, whereas the animals who had a lower stroke volume at 6 hours, 93% of them were dead by 72 hours. So the area under the curve was pretty good, 0.83. We used this model to do some further experiments, and this is where we fluid loaded the animals. So we made them septic or not, and we looked at time 0, which was 6 hours into the experiment. And the black show the eventual non-survivors, the diamonds show the septic survivors, and the circles show the healthy control animals. So you can see those who are going to die at baseline had a much lower amount of stroke volume. And then what we did, every 10 minutes, we gave a fluid challenge, and then another fluid challenge, and then another, until the animals died. And we were measuring with echocardiography the stroke volume. So you can see the healthy animals basically tolerated 60 mils of fluid before they died. So these were 300-gram animals, healthy, and tolerated a lot of fluid. The septic animals we predicted would survive tolerated about 48 mils of fluid before they died, whereas the ones we predicted would die could only tolerate 30 mils of fluid So again, this study, I think, nicely shows the myocardial depression effect, which differentiates animals who will go on to live and animals who will go on to die. And we looked at other things in this model, and here I'll show a few measures where the black right down the very bottom are the healthy controls, the yellow are the predicted survivors, the red, the non-survivors. So you can see interleukin 6, interleukin 10 is much, much higher, or interleukin 6 rather, is much higher in the animals that go on to die. Whereas interleukin 10, they're both raised in survivors and non-survivors to the same degree. On the right is a patient study, nearly 2,000 patients with community-acquired pneumonia in America. And they found that the bloods taken on admission, if you had high interleukin 6 and high interleukin 10, you had about a 40% mortality in the next 90 days. On the other hand, if you had low levels of both cytokines, you had a 5% mortality. So like our rats, there was a very big difference in outcome depending on the levels. We did the same for troponin and BNP. So the animals at 6 hours who would go on to die had much higher levels of troponin and BNP, B natriuretic peptide, a marker of ventricular dysfunction. And looking at on the right, you've got some human studies where, again, patients coming to the emergency department, the troponin was much higher in the eventual non-survivors, as was the B natriuretic peptide. Let's just focus on steroids. I know there's been a lot of interest with steroids, with sepsis over the years, and with COVID, and I'll try and merge the two together. This is the last bit of the talk. So I was on this paper we looked a number of years ago. This was a 500 patient study around Europe, the Corticus trial, and we found giving steroids to patients with septic shock had no effect on mortality. We've recently published this meta-analysis of corticosteroid therapy in the ARDS. So these are patients with bad lungs, many of whom have had it because of sepsis. And you'll see that it's not overall statistically significant, but there's a trend to benefit if you give steroids to these patients. This is a nice mouse study done by Marcin Osakowski when he was working in the United States. And they had a mouse model of peritonitis, cecal ligation and puncture, and they took blood 6 hours after giving them the insult. And the animals who would go on to die in the next week had much higher levels of interleukin 6 than those who would survive, and other cytokines the same. And the anti-inflammatory cytokines, a similar message. So interleukin 10 levels were much higher at 6 hours compared to the animals who would go on to live, similar to what we saw in the rats and what the American pneumonia study showed. And they did another study where they gave dexamethasone. It was quite a big dose, and they gave it 8 hours and 32 hours after they gave them the peritonitis insult. And you can see here it had absolutely no effect on survival. They were virtually identical, a failed trial. However, because they had previously found the interleukin 6 level was a good discriminator of survival, they measured interleukin 6 before they gave the steroids. And in the group predicted to, whoopsie daisy, in the group predicted to die, those who got the steroids showed a significant improvement in mortality. Whereas on the other hand, those animals predicted to live, the steroids actually made them worse. Wasn't significant, but there was a trend to an increased mortality. And so they concluded that, yes, there was a short-term benefit only in those patients predicted to do badly, but on the other hand, the opposite was seen in survivors. So let's move on to COVID. No doubt you're familiar with the recovery trial on dexamethasone, and this is a study mainly done in the United Kingdom, where they gave 2,000 patients dexamethasone over 4,000 patients standard of care. And they found there was a significant reduction in mortality in the patients who got the steroids. However, this was not in all groups. It was in the sicker end of the patient spectrum. So if you look at the odds ratios, the patients who were invasively ventilated at the time they started the dexamethasone had a big outcome effect. Nobody's been able to reproduce this study, but there was a 30% reduction in mortality at 28 days. On the other hand, if you started the steroids and you were just on oxygen, there was a significant benefit. However, if you were given the steroids and you weren't on oxygen, these patients did worse. So you'll see there's a trend. It's not significant, but there's a clear trend towards harm. So why is it that some patients benefit from steroids, others don't? We don't have the answer yet. But these patients were only 15% of the total, and many of them were still in hospital at 28 days. We don't know what happened to them. There's been some work recently looking at what these subphenotypes. So this is a lady, Carolyn Calfee in San Francisco, who's done this work, and they could divide patients into inflamed and the red hyperinflamed phenotype. So the hyperinflamed had a higher temperature, worse renal function, higher interleukin-6 levels, lower bicarbonate, lower blood pressure, lower urine, lower albumin, etc. So you had the less sick inflamed and the very sick hyperinflamed. And they found, looking at previous studies of fluid therapy, that the patients who were in the inflamed group, the not so sick group, had essentially a better outcome if you gave them more fluid, whereas the opposite was seen in the animals who are hyperinflamed. If you gave a liberal fluid strategy, they did worse. This has recently been applied in COVID patients, and this is a paper from China. And as you can see here, overall, steroids generally had a positive effect, though in some groups only, just like the recovery trial. So men benefited, women didn't benefit, if anything, a bit of a signal to harm. If you were more sick, a higher SOFA score, a severity of illness score, you did better than if you were less sick. And if you had worse lungs, you did better. So these patients generally did better if they were sicker. Likewise, if they were on a ventilator, they did better, not quite significant, but better than those who were not on a ventilator. So very similar to the recovery trial I showed you earlier. But then they split patients into this hypo and hyperinflammatory phenotype, and they found the steroids worked very well in the hyperinflammatory phenotype. They didn't work at all in the hypoinflammatory phenotype, if anything, a signal to harm. And when you compare that against the dexamethasone COVID recovery trial, the ICU patients, there was an approximate 40-50% reduction in mortality, whereas those who were given the drug on the ward or were less inflamed, there was a trend in the opposite direction, not significant, but a 15-19% trend to harm. So how do we put all of this together? So with our current animal models or patients, we lump every animal, every patient together, the survivors and the non-survivors. And we do the trial and the placebo, and there's no mortality benefit. Perhaps it would be better to divide the patients in those we think will go on to live and those who will go on to die. The non-survivors, here we can look at the mortality benefit. These patients should have a high mortality. We can see if the drug has any effect in reversing mortality. Whereas those patients who are predicted to survive, if they're going to survive, a drug looking at mortality benefit will not show much of a difference. So in these patients, we want to show a morbidity benefit. They get better more quickly, and clearly you need to look at safety. So that, to my mind, is a better way of doing it, which we can do in animal models. So in summary, I think we need to create good models, animal models, that are representative of human beings. And we've got to think about what insult, how severe, how long, and we can stratify our approach to drugs, devices, whatever, in animals, and then because the animal models are representative, we can move to humans and hopefully improve chances of outcome benefit in patients. I'll finish there. Sorry for overrunning. I'm delighted to hand you back to Felipe.
Thank you very much, Marvin, for your great talk. As usual, a great talk. I think that we got some questions from the audience. Just let me check here in the chat. It's quite difficult to use this. Yeah, it's a student from São Paulo. And I would love to ask whether the future of sepsis studies indicates any treatment that could impact on sepsis in the initial events of the disease. Does a early treatment would impact on sepsis outcomes?
Yeah. So I think so. I think there are, and we're doing some work, and others are. Can you identify sepsis before the patient becomes ill? And there are some, transcriptomic signals that, because obviously the patient's got to deteriorate before the doctor notices. The patient is usually at home for a day or 2 or 3 days before they feel sick enough to go to the hospital. So we've done some studies. This is in post-operative surgical patients where we've taken lots of blood. And again, you can find a signal. You can identify these patients early. And it makes sense that if you can identify them early, you may be able to intervene to stop the infection from becoming, sepsis and obviously causing death.
Okay, thank you. There is a question from a professor from São Paulo. I think that you knows her. She's Maria José. He's saying it's a pleasure to hear you. And I don't know if you can see the question in the chat.
Yeah, I can.
And she asked, what about surviving rates in animals? If you can follow them for 10 or 20 days? Or...
Yeah. In my experience, the trouble is with bacterial sepsis, our experience is they either die or live within 3 or 4 days. So you can, if they get through that period, even though they still have active infection, they develop tolerance, and so they're actually clinically improving. We've used Zymazan, which is a yeast cell wall product, and that gives a much longer peritonitic insult. So in these models, they're not survival, but they're more long-term critical illness. This model we've run for 2 or 3 weeks, and they get ill, they don't eat, they lose weight, they lose muscle bulk, they get inflammatory changes, and slowly over 2 weeks they recover. So you can do it, but in my experience, the rat models tend to not last. If you're doing a very severe bacterial insult, my experience is they tend to last no more than 3 days or more, and then they either have died by then or get better.
Okay, thank you. There is a question from Guilherme.
Yeah.
It's a $1 million question. If you can explain the outcome, different.
Yeah. Wouldn't it be lovely? We've done some and published some transcriptomic work, and there are transcript differences. So you can see early on animals who, so basically it's the same signal, but more exaggerated. So you get more extreme changes in animals that go on to die. And a guy called Ray Langley has shown this years ago, about 10 years ago, in patients. So if you look at patients in the emergency department or the rats early on, they show the signature is more extreme in the patients who go on to do badly. So it's the same pattern, but just more extreme, both pro and anti-inflammatory mediators, metabolic markers, etc. So you can look across a whole range of everything. The pattern is the same, it's just the magnitude is greater in eventual non-survivors. So why some mice do and don't, I don't know. We find, for example, when we give peritonitis, we give an identical insult, and the animals who do badly have a much more inflamed peritoneum. So whether it's the local reaction that dictates how well they do systemically and survive, I don't know, but you do see a difference, and as I showed you earlier, between the animals who do well and animals who eventually do badly.
Do you think that in animals at least is a intrinsic difference between animals? There is some minimal difference when the investigator performs insult. Because the animals have a background that is quite the same.
Yeah,
and
no, indeed.
Quite different.
Yeah, so you may well be right. We found even in animals from the same litter, from the same mother, and they were born at the same time, they act differently. You're right, Felipe, it might relate to experimental technique and whatever, but we try really, really, really hard to standardize the insult, but even then they act differently. Some animals laugh it off and find it funny. Other animals become a bit miserable, and other animals become very ill.
I got one question. If you think that we can learn from COVID, because COVID is a single agent, at least at the very beginning, is a single organ failure, and you know quite precisely when the disease starts, when patients get worse, when patients get organ dysfunction. And this is quite different from what we can do in sepsis. We are different agents, more than one organ failure. The organ failure can be different between patients. One starts with the lung and one starts with the kidney. And can we, instead of use biomarkers to stratify patients, septic patients, we use a thing that is similar to COVID, that you can stratify patients by organ dysfunction or by any clinical parameter and not a biomarker?
Yeah, I partially agree, partially disagree. The big problem about COVID, I think we as a scientific community have screwed up. I think people were rushing to give drugs and go into trials too quickly, and we didn't think properly about the design of the trial, to know what dosing we should give, what patients would likely benefit, taking blood samples to follow them on and learn, understand the biology to allow us to see, like I showed you earlier, why do steroids help men but not women? And the same with tocilizumab. There's no effect on women, there's an effect on men. Why? And none of these trials have taken samples for people to try and understand the disease. And we know with COVID, as you say, it's one virus, all right, the variants of the virus, but essentially mainly one lung, one organ failure. But yet even within the disease severities, the biological phenotype is hugely different. So your, interleukin-6 levels, a lot of the time they're very low or normal. In a few patients, they're very high. yet they're the same clinical disease severity. So I think there are advantages to COVID, but they're not, to my mind, it's not a pure homogeneous disease.
Okay. And septic patients, do you think that you have a single biomarker, then you can just split them by interleukin levels, interleukin 6, for example, or it's just about the kinetics of the biomarkers, then you have to have every single different biomarker? How do you deal with that in translation?
But, I showed you in my animal model that, yes, you could use IL-6, but you can also use stroke volume, you can also use troponin, BNP, and we've got other, cholesterol is a good biomarker. So we've got lots of different biomarkers. So if you can measure something rapidly in your lab, in your animal model, and then prospectively validate it just to show that serum troponin or, measured quickly is a good biomarker, then you've got a very nice model that you can stratify into animals that will do well, animals that will do badly. And, as I mentioned at the end of the talk, there's no point giving a drug looking at survival if the animal's going to survive anyway, apart from a safety signal.
Okay, but when you translate to patient, do you think the same rule will apply? There are several different patients in the first day of ICU admission would be different in the second, in the third, and the drug that I can use in the first day, it can be different from if I have a delay in the administration, or then we will have to have a blood drop in a mass spec to have a big look at the difference in patients, or do you think you can have only one or two biomarkers that can split patients quite different from the very beginning, that this can keep for 1, 2, or 3 days after then?
Yeah. Again, we found, and there are, I've mentioned cholesterol, which I think is a nice example. Cholesterol drops when you're critically ill, whether you've got sepsis or trauma or acute heart failure, it drops. And the more it drops, the worse the outcome. So, and the patients that recover, the cholesterol tends to slowly recover over days. The patients who don't recover, it stays low. So again, that's one example of a prognostic that you can then use to say, okay, we'll only give, as I showed you that trial on steroids, we'll only give steroids to the hyperinflamed and see if that makes a difference in mortality, whereas the less inflamed, perhaps, we do a safety study, but we don't combine the two groups of patients into one big stew.
Okay, do you think that these biomarkers are only a surrogate for severity of the disease? Or it can be a precise medicine stuff that it can use the right drug for the right patient, or both, actually?
I think, to my mind, they're just markers, because I'll give you an example. We talked about interleukin 6 earlier, but the problem is it's the interleukin 6 that's there, and binds to a receptor. And so if the receptor's blocked, you have high IL-6, but it doesn't mean that the receptor is still active. So, and we assume that what's in the blood is the same as what's going on in the lung with a pneumonia. And that's the problem. But, in COVID, for example, cytokine levels are generally very, very low, except in a few patients where they're high. So should you give your interleukin 6 blocker to everybody, or just focus on the ones who are high IL-6 or etc.? So I think whether the biomarker is a direct, cause of the problem or a surrogate prognostic, time will tell.
Okay. Let me check if we have any other questions. Okay, I think we're good. And we have a great talk today, and I would like to thank to Professor Dr. Singer to hear us. I'm sure that everyone here really enjoys this talk.
Thank you very much. Yeah.
Ok. Thank you, Marvin. Para lembrar todos que tem um QR Code que foi solto, é isso, né, Carla? Para fazer a presença. And we're gonna talk something. Okay.
No, sorry, wrong hand.
Ok. Obrigado para todos, então. Foi um grande prazer ter todos aqui. Aguardo vocês hoje à noite para a abertura do evento e a continuidade do evento. Muito obrigado a todos.
Vivemos em um planeta interconectado, não apenas pela velocidade com que trocamos informações, mas porque tudo o que fazemos impacta na vida uns dos outros. Isso valoriza uma das coisas que mais nos faz humanos, o trabalho coletivo. Somos uma espécie de realizadores, com alta capacidade criativa, que pode sim mudar os rumos do planeta. Podemos fazer diferente usando a tecnologia para nos tornarmos mais eficientes, otimizando nossos recursos, evitando o desperdício e transformando a vida de todos. A Unesc acredita na conexão do conhecimento e da comunidade, da ciência e das grandes ideias, dos olhares e das diferentes realidades, de pessoas e propósitos inspiradores. Venha construir o amanhã com a gente. Unesc, uma universidade de conexões. Matrículas abertas para os cursos de graduação presencial.